Imagine you've just launched your app, it's running on a single server and things are going great until they're not. As your user base grows, that lone server starts hitting a wall. First, you run into hardware bottlenecks. Your CPU is spinning at 100% and your memory is completely tapped out. This leads to high latency where your users are stuck staring at loading spinners because the server just can't keep up with the requests. But the real nightmare is that the server is a single point of failure. If it crashes, your entire business goes offline. And since you can't keep making a single machine infinitely more powerful, you have hit the limit of vertical scaling. The solution for this is horizontal scaling. Instead of one giant server, we bring in a whole team of them. But adding more servers creates a new problem. How do you decide which user goes to which server? You can't just give users 5 different URLs to try, right? So basically, you need a traffic cop, like a mechanism that distributes traffic evenly so no single server gets crushed, and it should prevent overload by rerouting requests in real time. Also, it should handle failures automatically, so if one server goes down, your users never even notice. So this critical component is what we call as a load balancer. So what exactly is a load balancer? Think of it as a reverse proxy that sits in front of your server fleet. It acts as a single entry point for every single request coming from your users. The architecture is simple. The user sends a request to your domain, it hits a load balancer, and then the balancer intelligently hands the request off to one of your application servers, which then interacts with your database. But it's more than just a middleman, it's the brain of your infrastructure. It handles five critical responsibilities: traffic distribution, meaning ensuring no single server is doing all the heavy lifting while others sit idle; high availability, keeping the server online 24/7 even during maintenance; fault tolerance. If a server catches fire, the load balancer instantly reroutes the traffic so the user never even sees an error. Health checking. It's constantly pinging your servers to make sure that they are actually awake before sending them work. Scalability. It lets you add or remove servers on the fly without ever changing the IP address your users are connected to. Simply put, without a load balancer, a large scale distributed system isn't just inefficient, it's fundamentally unreliable. But a load balancer isn't just guessing where to send those requests. It follows a specific set of rules or algorithms to decide exactly where each user should go. There are several strategies used to distribute traffic, but let's start with one of the most famous one, round robin. Think of round robin like a dealer at a card table. It sends the first request to server 1, and the second to server 2, and the third to server 3. Once it hits the end of the list, it loops back to the beginning and repeats the cycle. The big pro here is that it is very simple. It's incredibly easy to implement and requires almost no configuration. However, it has one major con. It's blind to the actual server load. If server 1 is struggling with massive complex query while server 2 is sitting idle, round robin will still send the next request to server 1 anyway, potentially making a bad situation worse. To solve this, we need an algorithm that actually pays attention to what's happening on the backend. That's where least connections come in. The least connection algorithm is much smarter. Instead of just going in a circle, the load balancer looks at each server and asks, who is the least busy right now? It then routes a new request to whichever server has fewest active connections. The pros here are obvious. It's significantly better for uneven workloads. If some requests take 5 seconds to process and others take 50 milliseconds, this algorithm ensures that no single server gets bogged down while others are free. And the cons? There's a slightly higher overhead. The load balancer has to do a bit more thinking and record keeping to track exactly how many connections are open on every single server at all times. But what if your servers aren't identical? What if one of your servers is a beast with 64 GB of RAM while another is a smaller, older machine? For that, we use weighted load balancing. In weighted load balancing, we assign a specific weight to each server based on its hardware capability. For example, let's say server A is a powerhouse, so we give it a weight of 5. Server B is a bit smaller, so we give it a weight of 2. In this scenario, the load balancer will intelligently send significantly more traffic to server A, knowing it can handle the pressure, while only occasionally sending requests to server B. This is a go to strategy whenever you have a heterogeneous fleet, or simply put, when your servers have different hardware capacities. While these algorithms are great for distributing the work, they don't always consider the identity of the user. Sometimes it's vital that a specific user stays glued to a specific server for their entire session. For that, we turn to IP hashing. With IP hashing, the load balancer takes the client's IP address and runs it through a mathematical function, a hash, to map it to a specific server. Essentially, hash IP equals a specific server. The main pro here is that it has session persistence. By using IP hashing, you ensure that as long as you by using IP hashing, you ensure that as long as the user's IP doesn't change, they always hit the same backend server. However, the con is that you can end up with an uneven distribution. If a large number of users are coming from the same corporate gateway or a VPN, they might all be hashed to a same server, leaving your other servers bored while one is working overtime. Now, all these algorithms assume that the servers are actually working, but in the real world, servers fail. This is why load balancers perform continuous health checks. Think of it like a constant dialogue. The load balancer is perpetually asking the servers, are you okay? Can you still take the request? If a server fails to respond correctly, it automatically gets removed from the pool. Traffic is then instantly rerouted only to the remaining healthy servers so that the users never even knows that there was a problem. So how does it check? There are three common methods. The first one is the HTTP status checks. The balancer sends a request to a specific endpoint like slash health and waits for a 200 OK status. TCP connection test. It attempts to open a connection on a specific port to ensure that server is still listening. And the third one is the heartbeat monitoring. It's a simple periodic signal sent between the balancer and the server to confirm life. This proactive monitoring is what prevents your system from sending requests into a black hole of failed servers. So we have the logic and we have the monitoring, but to truly understand how to implement this, we have to look into the where, that is the specific layers of the OSI layer where load balancing happens. First up is layer 4 load balancing, which operates at the transport layer. This means the load balancer is making decisions based purely on network level information, specifically IP addresses and TCP or UDP ports. The biggest advantage of layer 4 is speed because it doesn't need to look inside the application data like the actual contents of the HTTP request. It can route packets almost instantly. It's incredibly lightweight and efficient. A classic real world example of this is the AWS Network Load Balancer. It's designed to handle millions of requests per second with ultra low latency, making it the perfect choice for high performance TCP traffic where you don't need to inspect what's actually inside the message. But what if you need to be more surgical? What if you need to reroute traffic based on what user is actually doing? For that, we move up to layer 7. Layer 7 load balancing operates at application layer, specifically focusing on HTTP and HTTPS traffic. Because it understands the application protocol, it can look deep inside the request to make routing decisions based on URL paths. For example, sending all traffic for slash API to your API fleet while sending slash videos to specialized video processing servers. HTTP headers in like identifying different types of clients or devices, or cookies like managing advanced session affinity or alpha beta testing. This gives you incredible flexibility for complex architectures. This is where tools like Nginx, HA Proxy, and AWS Application Load Balancer shine. While it's technically slower than layer 4 because it has to decrypt and inspect the traffic, the intelligence it provides is often worth the trade off. Throughout this video, we've talked about load balancers, but in modern architecture, these are often a specific implementation of a reverse proxy. A reverse proxy sits between your clients and your backend servers, ensuring the clients never know the backend servers exist. Beyond just balancing load, it provides SSL termination to handle encryption, caching to serve content faster, security filtering to shield your servers, compression to save your bandwidth. Whether it's Nginx, Envoy, or HA proxy, the goal remains the same: a system that is fast, secure, and always reliable. But there is another side to this, the forward proxy. While a reverse proxy protects the server, a forward proxy sits between the clients and the internet. Think of a corporate network or a school. When you try to visit a website, your request goes to the forward proxy first. It's used for corporate filtering, that is, blocking specific websites, access control, that is, managing who can go where, anonymous browsing, hiding the client's true IP from the internet, caching, that is, saving bandwidth by storing frequently accessed web pages. Essentially, a forward proxy hides the client while a reverse proxy hides the server. This, this leads to a common question: what is the actual difference between a reverse proxy and a load balancer? Think of it like this: a reverse proxy is a gateway. Its primary job is to be the face of your backend servers, handling tasks like SSL and caching. A load balancer is a specialist whose primary job is just distribution. In practice, modern systems don't choose one or the other, they kind of combine them. Tools like Nginx, HA proxy, or Envoy acts as both. They provide the security and routing of a reverse proxy while simultaneously using load balancing algorithms to distribute traffic across your fleet. In a real world large scale system, you aren't just using one of these components, you're using all of them in a coordinated chain to ensure maximum performance. The flow somewhat looks like this: the user makes a request, it first hits the CDN, that is the content delivery network for static files like images. If it's a dynamic request, it hits the load balancer to find the right server cluster. It then passes through a reverse proxy like Nginx for security and SSL termination. It reaches the application server to process the logic. The server checks a cache like Redis for speed before finally hitting the database. This layered architecture is the gold standard. It's what gives modern apps their scalability, reliability, and ultra low latency. To wrap things up, remember these core points. Load balancers are the key to traffic distribution and horizontal scalability. Proxies are the gatekeepers that control exactly how traffic flows through your system. Together, they provide the high availability, fault tolerance, and security that modern distributed systems demand. They aren't just nice to have, they are the fundamental building blocks of the modern web. Thank you. I'll see you in the next one.